have you ever stopped to think about how your smartwatch just knows things? Or how your car's safety features can react way faster than a human ever could? Well, it's not magic. It's actually a tiny, incredibly powerful brain hidden inside. Today, we're going to pull back the curtain on the unsung hero of our digital world, a little piece of tech that's in billions of devices you use every single day, but that you've probably never even heard of. Let's jump in. So think about it for a second. You've got your car with all its complex electronics. You've got your fitness tracker, which is constantly measuring your heart rate. And you've even got your coffee maker, which knows exactly when to start brewing. On the surface, they're completely different things, right? But they all share one fundamental secret. And there it is, the ARM Cortex M processor. Now, this isn't the kind of monster chip you'd find in a high-end gaming computer. No, this is something different. It's a microscopic powerhouse, built for one purpose: to be a dedicated brain for a single device, and to do that job with incredible efficiency and reliability. It truly is the quiet workhorse of the modern world.
So what's the secret sauce? What makes this little chip so special? Well, here's how we're going to break it down. First, we'll look at just how widespread these things are. Then, we'll take a peek inside its internal toolkit. We'll explore how it runs in different modes, check out its super organized memory, and finally, we'll connect it all back to why this design is so important in your day-to-day life.
First up, the tiny brain everywhere. And, I'm really not exaggerating when I say that. These Cortex M processors are literally the backbone of our connected world. They're in your smart thermostat, your doorbell camera, your headphones, and they're also in the heavy-duty industrial robots that build our cars. The reason they're so popular is that they hit this perfect sweet spot between solid performance and ridiculously low power consumption. That makes them the go-to choice for any device that needs to be smart, reliable, and run for a long, long time.
Okay, so we know these chips are everywhere, but how do they actually think? To get that, we need to look at the CPU's internal toolkit, basically the set of rules it lives by. In the engineering world, this is called the program model, and it defines absolutely everything about how the software talks to the hardware.
You can think of the program model as the processor's fundamental DNA. It's the blueprint that lays out how it behaves, from the tiny storage spots called registers to its different operating modes, all the way down to how it executes every single command. If you're a developer working close to the metal, understanding this blueprint is everything. And right at the heart of that model, you'll find the registers. The best way to think about these is as the CPU's own personal workbench. They're super small, lightning-fast little storage spots right on the chip where it keeps the exact data and instructions it's working on right now. It's like having all your tools laid out right in front of you, ready to go in an instant. And we can actually make this really simple with a few analogies. You've got the general-purpose registers, which are like a worker's scratch pad for quick calculations. The program counter, that's the CPU's to-do list, always pointing to the very next task. The stack pointer acts like a filing system, keeping memory organized. And the link register is my favorite. It's like a go-back bookmark, so the CPU always remembers where it was before it got interrupted.
Let's see that program counter in action. So imagine your smartwatch is just doing its thing, running its main clock face program. Suddenly, you press a button. Boom, that's an interrupt. Instantly, the program counter drops what it's doing and jumps to a special little piece of code for handling that button press. Once that's done, the program counter just jumps right back to where it left off, and the clock face carries on like nothing ever happened. It's just a beautiful, efficient way to handle real-world events.
And that brings us to something really critical. To keep the whole system running smoothly and securely, the Cortex M doesn't just have one mode. It has different operating modes, each with its own level of power and access. It's a built-in security system, and it's absolutely essential for protecting the device from glitches or even attacks. The two main modes are Thread mode and Handler mode. Here's a great way to think about it. Thread mode is for your normal, everyday applications. It can be set to unprivileged, which means it has limited access. It can't just mess with the core parts of the system. Handler mode, on the other hand, is for the important stuff, those interrupts and exceptions we talked about. It's always privileged, which means it has full keys to the kingdom, so it can handle critical tasks without any interference. Okay, so the processor has its rules and its different modes. But where does it keep all of its stuff? The code, the data? Well, that's where its incredibly well-organized memory system comes into play. It's not just a big, empty space. It's a smart and efficient workspace.
Moving data around efficiently is the name of the game. So the Cortex M uses this clever system with two different roads. Think of it like a city.
The really important, high-speed stuff like memory gets to use a super-fast highway called the AHB bus. Meanwhile, the slower things, like simple sensors and ports, use the more energy-efficient local roads. That's the APB bus. This way, you don't get traffic jams, and everything moves at the right speed.
And this design choice has some huge payoffs. You get faster access to your code and data, you clear up potential bottlenecks, you get way better performance for time-sensitive tasks, and you end up using less power. It's a win all around.
But wait, it gets even smarter. The system also uses something called memory attributes. These are basically special labels that developers can stick on different areas of memory. These labels are instructions for the CPU telling it exactly how to handle the data in that region. It's a powerful way to fine-tune the system for maximum speed and security.
So, what kind of labels are we talking about? Well, you can mark a region as cacheable, which tells the CPU to keep a speedy copy nearby. You can mark it as executable, which is a simple yes or no on whether code can be run from there. Shareable is for data that multiple parts of the system need to see. And bufferable helps speed things up when you're writing a lot of data at once.
Now, that executable label is a total game changer for security. Just by marking a region of memory as non-executable, you can completely shut the door on a whole category of cyber attacks where a hacker tries to sneak in their own malicious code and trick the system into running it. It's a simple, elegant security feature that's baked right into the hardware.
All right, we've gone pretty deep into the technical weeds here, so let's pull back up for the big question. Why does any of this stuff actually matter to you? How does this clever design translate from technical specs into your daily life?
When you boil it all down, the entire design philosophy of the Cortex M rests on these three pillars. It's not about being the absolute fastest chip on the planet. It's about delivering a perfect balance of performance, incredibly low power usage, and rock-solid reliability.
And this is the result. This clever design is the reason your fitness tracker can last for a week on a single charge. It's why your car's anti-lock brakes can react in a fraction of a second. It's why your smart home devices are both dependable and secure. And it's why industrial machines can perform tasks with pinpoint precision over and over again.
So in the end, the Cortex M really is a masterpiece of engineering. It's this incredible, masterful balance of power and efficiency scaled up and put into billions of devices that truly makes our modern, connected world possible. So we've seen how this tiny brain has shaped the world we live in today. But what about tomorrow? As our world gets even more connected, with AI and machine learning pushing into every device, what do you think is the next big challenge for these tiny brains? What comes next?